So, in the previous section, I mentioned at the very beginning that with chapter 5, one of the things that makes this a little bit tricky of a chapter is that there's going to be a lot of different rules as we progress through chapter 5. So, in section 5.2, we're actually going to be looking at three of those rules. We're going to be looking at two addition rules. These two rules aren't going to be too bad. They're pretty similar to each other. And also, another nice thing about the addition rules is that we're going to have a keyword. So, whenever we see this keyword, we know to use one of the two addition rules. And then the other rule that we're going to introduce in this section will be this idea of the complement. So, we just touch upon it and introduce the complement in this section, but we're going to use it a lot more heavily in the next section, actually. Hey, but let's start off with discussing our addition rules here. Hey, so in order to discuss the first addition rule, we first need to know what we mean by disjoint events or mutually exclusive events. So let's look at that definition first. Hey, so it says here that two events are disjoint. Okay, so two events will be disjoint if they have no outcomes in common, so nothing in common. And another name for disjoint events that we should also know would be mutually exclusive. Okay, so disjoint and mutually exclusive events mean the same thing. Both of those things will tell us that the two events will have no outcomes in common. Okay, so then let's go ahead and look at our first example here, where it says a probability experiment is conducted in which the sample space for the experiment will be all of these numbers here. So this is going to be our sample space, which is just 0 to 10. And then they're going to define a few events here. Hey, so they're telling us to let event E have 2, 4, 6, and 9. So those are going to be our outcomes in event E. And then here is our event F that will have the outcomes 0, 1, 3, 7. And then lastly, our event G, which has the outcomes 1, 4, and 5. Hey, so for part A, it's asking us to list the outcomes that are in E and F. And then from there, it's asking us are E and F mutually exclusive, which was just the definition we saw before. So again, mutually exclusive means that they have no outcomes in common. But let's go ahead and first list the outcomes in E and F. Okay, so if we want to list the outcomes in E and F, that means I want to focus on these two events that we have right here, E and F. And then if we're looking for the outcomes that are in E and F, all that means is we're trying to see what outcomes are both in E and also F. So what's in both of them? What do they have in common? Hey, so looking at our outcomes in event E and our outcomes in event F, you'll see that they actually don't have anything in common. So there aren't any outcomes that are both in E and also F. So the way that we would denote that is we would have our French braces, but we wouldn't have anything inside of them because there's nothing in E and F. There's nothing that they have in common. Hey, so answering the last part's asking again, are E and F mutually exclusive? Well, remember the definition of mutually exclusive or disjoint is that they have no outcomes in common. And that's what we're seeing here with these two events, E and F, is that they don't have any outcomes in common. So then we would say that yes, they're mutually exclusive. Or again, another term for mutually exclusive is disjoint. Hey, so again, since E and F, if you look at those two events, they don't share anything, they don't have anything in common, so that's why we would say they're mutually exclusive or disjoint. Hey, so then now let's do a similar thing for part B. Hey, so it's asking us to first list the outcomes that are in E and G, and then from there we're going to decide if E and G are mutually exclusive. Okay, so looking now at our events E and G, we again want to see what's in E and G. So what's in both of them, what they have in common. So looking at E and G, they do actually have something in common, and then that's going to be the 4. Okay, so the 4 is in both E and G. Okay, so then now answering this last part, if E and G are mutually exclusive, well, here we can see that E and G do have something in common. So since they do have something in common, we would say that they're not mutually exclusive. Or again, we could also say not disjoint. Okay, so if they do have something in common, then we would say that they're not mutually exclusive or not disjoint. All right, so then now let's look at our first rule in this section, and that's going to be called the addition rule. But this addition rule that we're looking at only works for disjoint events. So it only works for events that do not have anything in common. After we go over a few examples of using this addition rule, where again the events are disjoint, they don't have anything in common, then we'll look at another addition rule for when they do have things in common. What would we have to do there? Hey, but this addition rule that we're looking at will only work for disjoint events, only for events that have nothing in common. Hey, so it says here if E and F are disjoint or mutually exclusive, so again, nothing in common, then let's say it asks us in the problem to find the probability of E or F. Okay, so that means we want event E to happen or we want event F to happen. How you would find that probability is by just simply adding. That's why we call it the addition rule. All you would have to add together is the probability of E plus the probability of F. Okay, so again, if you have two events that are disjoint, nothing in common, how you would find the probability of E or F is by just adding the two probabilities together, the probability of E plus the probability of F. Okay. And then this works, what this note is saying is that this works for not just two events, but let's say you have several events and all of them are going to be disjointed from each other, then this works for more than two events as well. Okay, so I mentioned a key word earlier at the beginning of this section. So the key word for addition will be or. So whenever you see the key word of or, that's going to tell you to add. Okay, so then let's go ahead and start looking at some examples where we will have to use this addition rule. Again, this one will only work for disjoint events. Hey, so it says, suppose we are drawing a single card from a standard 52 card deck. So we dealt with the deck of cards in the previous section. So let me actually pull up that image that we saw before. Hey, so this is from the 5.1 notes where we were dealing with the deck of cards here. So I'll refer back to this image just in case, again, some of us aren't too familiar with using the deck of cards. It's nice to have a picture of it. Hey, so it says again, we're drawing just a single card from a standard 52 card deck. So for part A, it says to find the probability that we draw a 4 or a jack. So we want a 4 or a jack. Okay, so what I'm going to do is whenever I see the keyword, I'm going to circle it. Okay, and it's going to seem kind of excessive at this point because it's really the only keyword that we've seen so far, and we're going to see it over and over and over again. But I just really want to hammer it in that this is going to be a keyword, and when we see the keyword, we want to add. So again, whenever we see the keyword of or, this is going to tell us to add. Hey, so the two events that we're dealing with here, we're dealing with the event of drawing a four or a jack. Four or a jack. Okay, so those are the two events that we're dealing with here. Okay, so if I go back to our image of the deck of cards, because I want to again make sure that these two events are disjoint. They don't have anything in common, drawing a four and drawing a jack. Hey, so going back to the image of our deck of cards, hey, so here are all of our fours. Hey, and here are all of our jacks. Hey, and then you can see that they're disjoint. There's not a card that they have in common. There's no sort of overlap between these two groups. Hey, so since drawing a four and drawing a jack are disjoint, nothing in common, that means we could just simply add. Hey, so we have, from the image that we saw before, we have four fours. Hey, or tells us to add, so then plus, we also have four jacks. Okay, so then we would just add those two together. We would get 8. Okay, and then remember, you still always, like before, have to divide by the total. And then remember, we had a total of 52 cards in the deck. So we still have to divide by our total of 52. Okay, so then let's go ahead, type this into the calculator to see what we'll get as our decimal answer. So again, I do want to see work like what I'm showing here on your homework. I don't just want to see the final answer. Okay, so let me clear out of all of this from before. Okay, and then just typing in 8 divided by 52 to get our decimal answer, which I'll just round to the third decimal place. I'll round to right here. Okay, so since there's an 8 that comes after the 3 will get bumped up to a 4. So we're getting a probability of 0.154. Okay, or about a 15% chance of drawing a 4 or a jack. Okay, so then now let's look at part B, asking us to find the probability that we draw a black card or a red card, black or red. So again, we see the keyword of or. Okay, so then that's going to tell us to add. Whenever you see or, we'll add. Okay, and then the two events that we're dealing with here is drawing a black card. That's one of our events. And then the other event is drawing a red card. Hey, so let's go back to our image of the deck of cards. Again, make sure that these two events are disjoint, nothing in common. Hey, well, here are all of our black cards. And then here are all of our red cards. Okay, and then you can see again that these two groups have nothing in common. There's no overlap between the two groups, so that means they are disjoint. So then that means we can just simply add the two numbers together. Okay, so remember you'll have 26 black cards because you have the 13 clubs and the 13 spades, so 26 black cards, and you also have 26 red cards because you have your 13 hearts and the 13 diamonds. Okay, so then just adding, since again they're disjoint, we have 26 black cards, or tells us to add, so then plus. We also have 26 red cards. Okay, so then if we add all of that together, we would end up getting 52. But remember, it's a probability that we're finding. So probability is always going to be a decimal number. So we'll have to divide by our total, which is 52. And 52 divided by 52, that's just going to give us 1. Okay, or as a percent, that would just be 100%, which makes sense because when you're drawing a card from from the deck of cards, it's a 100% chance that it's either going to be black or red. Okay, so then now looking at part C, we want to find the probability that we draw an ace, a king, or a queen. Ace, king, or queen. So again, let me circle my keyword of or, which again tells us to add. Okay, and then here we actually have three events. So we have the event of ace, our next event is king, and then our last event is queen. So ace, king, or queen. Okay, so if I go back to our picture of the deck of cards, here are all of our aces. Here are all of our kings and then all of our queens. Hey, so looking at those three groups, notice that all three of those are disjoint. Again, we have nothing in common, no overlap between those three groups. So then that means we can just simply add the numbers together. And notice you have four of each. You have your four aces, four kings, and four queens. Okay, so aces, we have four aces, plus we also have four kings, plus lastly we have our four queens. Okay, so then adding all of that together, we would end up getting 12. But remember, with probabilities, we'll have to divide by the total, which in this case is 52. Okay, and then typing this into the calculator to get our decimal answer, which I'll round to the third decimal place here. So since there's a 7 that comes after it, the 0 is going to get bumped up to a 1. So we're getting a probability of 0.231. Okay, or about a 23% chance of drawing an ace, a king, or a queen. All right, so then now for part D, it says to find the probability that we draw a heart or an ace. Okay, so let me again circle our keyword of or, which will tell us to add. Okay, or add, or will tell us to add. Okay, and then the two events that we have here will be heart, so drawing a heart, and then our second event is drawing an ace. So heart or ace. Hey, so then let's go ahead to, again, our picture of the deck of cards because I, again, need to make sure that these two events are disjoint, that they don't have anything in common. Hey, so here are all of our hearts. Hey, and here are all of our aces. Hey, so for this one, you actually see that these two events, heart and ace, are not disjoint. They do have something in common. Hey, so since these two events are not disjoint, I can't use the rule that we've been using. Because again, that rule that we've been using only works for disjoint events, only works for events that don't have anything in common. But we can see with these two events of heart and ace, we do have something in common. So at this stage, we're not able to do this problem since they're not disjoint. Okay, so what's going to happen is we'll introduce our second addition rule that will help us work with events that are not disjoint like what we're seeing here. So we'll actually come back to this example later. Hey, but at this stage with the rule that we've seen so far, we can't right now do this problem since they're not disjoint. They do have something in common. Okay, so then now let's go ahead and look at our next addition rule called the general addition rule. So the reason why we call it the general addition rule is because it's going to work for any two events, any two events. So that means if the two events are not disjoint, if they do have something in common, like what we saw earlier, then we would be able to use this rule. Okay, so if you have any two events, E and F, then how you would find the probability of E or F is you would still add your probabilities together. Okay, so that's similar to what we were doing before. We would add the probabilities together. Hey, but now this is the extra part where you will also have to subtract. You're going to have to subtract the probability of E and F. E and F. So remember, E and F, that represents what they have in common. Hey, so the only thing that's going to be a little bit different here is, okay, we're still going to add the two probabilities together, but we want to subtract out what they have in common. Okay. Okay, so if they have, let's say, two cards in common, you would have to subtract out those two cards. If they have five cards in common, you would have to subtract out that five. Hey, so the only difference here is, yes, you're still going to be adding, but you want to subtract out what they have in common. Hey, and you still have, though, the same keyword of or. We'll still see that same keyword of or, which again still tells us to add. We'll just have to be careful. And if the two events are not disjoint, if they have anything in common, we'll make sure to subtract that out. And you'll see why we do that is because that's going to take care of any double counting of the stuff that they do have in common. We don't want to double count anything. So that's going to take care of that, this subtraction part. Okay, so then let's go ahead to the next page. Hey, so similar experiment here. We're still drawing a single card from a standard 52 card deck. Hey, so part A, this is actually the one that we said we couldn't do at the time, but now that we have this general addition rule, now we'll be able to find this probability. So we want to find the probability that we draw a heart or an ace. So let me still circle the keyword. So keyword of or tells us to add. Hey, and then our two events here are again heart and then ace. Heart and ace. Hey, so then going back to our image of the deck of cards. Hey, so we have our 13 hearts. Then or tells us to add. We want to add our aces. Hey, so then we have our four aces. Hey, but remember, we have to subtract for this one because they do have something in common. So we do need to subtract because you'll see what happens here is when we add together our 13 hearts, we got all 13 of these cards, and then we added to it all four of our aces, you can see that we double counted something. Hey, and the thing that we double counted was what they had in common. We double counted this ace of hearts, the card that they have in common, we counted it twice. We counted it with the hearts and then we counted it again with the aces. So then that's why we have to subtract that one card out since again it got double counted with the two groups. So that's why we'll always, if the two events do have something in common, if they're not disjoint, we'll have to subtract out what they have in common to again take care of that double counting. Okay, so in this case, they only have that one card in common, the ace of hearts. So we'll have to subtract that card out. Okay, so then adding and subtracting all of this, we end up getting 16. But remember, we still have to divide by our total of 52. Okay, and then putting this into the calculator, rounding to the third decimal place. Since there's a 6 that comes after, the 7's going to get bumped up to an 8. So we're getting a probability of about 0.308, okay, or about 31%. So about a 31% chance of this happening. Okay, so again, just be careful if there is anything in common, make sure to subtract it out. Okay, so now for part B, it says to find the probability that a red card or a diamond is drawn. Okay, so let me circle our keyword of or, which will tell us to add. Okay, and our two events here are red card and then diamond. Red card, diamond. Okay, so then going back to our deck of cards. Hey, so here are all of our red cards. Okay, so then notice you have 26 of those. Okay, or tells us to add, so then plus. Now I need to add to it all of my diamonds. Hey, well, here are all of my diamonds. And we had 13 of those. Hey, and then you can see if I go back to our picture, you can see that there is an overlap. There are cards that they have in common, and the cards that they have in common, the cards that we double counted were actually those 13 diamonds. As we counted those 13 diamonds with the red cards, and then we counted them again with the diamonds. Hey, so since I double counted those 13 diamonds, we actually have to subtract that out. Okay, so subtracting out those 13 diamonds that we double counted. And then if you add and subtract all of this, we end up just getting 26, which we have to still divide by our total of 52. And you'll see if you type that into the calculator, you end up just getting 0.5 or a 50% chance. Okay, so then for part C, we want to find the probability that a black card or a diamond is drawn. Black card or a diamond. Hey, so again, circling our keyword of or, which tells us to add. Hey, and then the two events that we're dealing with here, black card and then diamond are two events. Black card, diamond. Black card or diamond. Okay, so looking at our deck of cards, here are all of our black cards. Hey, so then we have 26 black cards because you have your 13 clubs and your 13 spades. So we have our 26 black cards, or tells us to add. So then plus, now I need to add to that all of my diamonds. Okay, so then here are all of our diamonds. Remember, we have 13 of those. Okay, and then let's look back to see if there's anything we should subtract, if they had anything in common, anything we double counted. Hey, but between our two groups of black cards and diamonds, you can see that there's no overlap. They don't have anything in common. So since they don't have anything in common, that means I don't have to subtract anything out. There wasn't anything that we double counted. Hey, so these two events are disjoint. So when they are disjoint, nothing in common, all you have to do is add. You don't have to worry about subtracting since they don't have anything in common. We didn't double count there. Hey, so if we add, we end up getting 39, which we again have to divide by our total of 52. And then if we divide those two, let me just give you this number, we would end up getting exactly 0.75, dividing those two in the calculator. Okay, so then now looking at part D, we want the probability that a heart or a face card is drawn. Heart or a face card. Hey, so again, we have our keyword of or, which will tell us to add. Hey, just really trying to hammer that in, that the keyword of or tells us to add, so that's why I keep doing that over and over again. Hey, and then our two events here will be heart and then face card. Okay, so then looking at our deck of cards, here are all of our hearts. Okay, so we have 13 of those. Or tells us to add, so then plus, now I need to add to it all of my face cards. Okay, well, here are all of our face cards. Okay, and then we actually have 12 of those, 12 face cards. Okay, and then let's look back to see if there's anything that we should subtract, anything that they had in common, any sort of overlap. Hey, well, looking at our two groups, we actually do have some overlap here. Hey, so the overlap, what they have in common will be these cards that we have right here. Hey, so then they have 3 cards in common that we'll have to subtract out. Okay, so then adding and subtracting all of this, we would end up getting 22, which we would divide by our total of 52. Okay, so then rounding to the third decimal place, this will just round to be 0.423 since there's just a 0 that comes after 0.423. Okay, or about a 42% chance of this happening. Okay, so then now looking at part E, we want to find the probability that we draw a red card or a face card. Okay, so here's our keyword of or, which will tell us to add. Okay, and then we have our two groups here, red card and then face card, red card and face card. Okay, so then looking at our deck of cards here are all of our red cards. And we have 26 of those since you have the 13 hearts and the 13 diamonds. So we have 26 red cards. Plus, now we want to add to it all of our face cards. Okay, well, we have these 12 face cards. Okay, and then we will have to subtract their were cards that they had in common. So then let's go ahead and subtract that out so we're not, again, double counting. So then you can see that we have these 6 cards in common. Okay, so we double counted those 6 cards, so then make sure we subtract those out to, again, take care of any double counting that we did. Okay, so now adding and subtracting all of this, we would end up getting 32, which we divide by our total of 52. Okay, and then putting this into the calculator. Okay, and then rounding to the third decimal place, since the 3 comes after, this will just stay. So then we're getting a probability of 0.615, or about a 62% chance of this happening. Okay, so again, for your homework, make sure you are showing this work here of what you're adding and possibly subtracting. Again, don't just give the final answer here. Okay, so then now for part F, we want to find the probability that a black card or a 7 is drawn. So again, keyword of or tells us to add. And then the two groups that we're dealing with here is black card and then 7. Okay, so then going to our deck of cards here, we have here our black cards. So we have 26 black cards. Or tells us to add, so then plus 7s. Here are our 7s. Okay, so then we have 4 7s that we should add. Okay, and then we will also for this one have to subtract. There were cards that they had in common that we double counted, so we'll have to subtract that out. Hey, so in this case we have these 2 cards in common that we double counted, so then make sure we subtract that out. Okay, and then adding and subtracting all of this, we get 28, which we have to divide by our total of 52. And then let me just give you the decimal answer for this. So if you were to type this into the calculator, you would end up getting 0.538 as your decimal answer, rounded to 3 decimal places. Okay, so we will use this rule a little bit later on in a slightly different way, looking at a table of data instead, but we will use this rule again later on. So keep that in mind. And whenever you see the keyword of or, we will always add, but if there's something in common, some sort of overlap, we would have to subtract that out. Okay, so keep that in mind. That will come into play later on. But let's go ahead now to the next page and start looking at the complement. Okay, so like I mentioned earlier, the complement is going to be something that we introduce in this section, work with it just a little bit, but in the next sections where we're really going to hit this rule pretty heavily. Hey, so let's first look at the definition for complement. Hey, so it says here to let S denote the sample space of the experiment. So remember, the sample space, that's just all possible outcomes. Okay, so S is going to denote the sample space, and then E is just going to denote some event. Okay, then the complement of E, okay, which we denote this way, E, since it's the complement of E. So we use an E, and then to denote the complement of the event E, we use kind of like an exponent of C. Okay, so that's how we'll denote the complement of E. Hey, and what the complement of E will be, it's going to be all the outcomes in the sample space that are not in E. Okay, so it's essentially going to be everything else in the sample space that's not in your event E. Hey, so another way that you can kind of, and it's not exactly the same, but a way that you can kind of think of the complement to kind of help you understand it, it's kind of, this is why I'm putting quotations around it because it's not exactly the same, but it's kind of like the opposite of your event E, the opposite of E. Okay, so then let's look at a couple of examples here of finding the complement. So it says, suppose our experiment is rolling a fair die, rolling a fair die. Hey, so for part A, it's asking us to find EC, so find the complement, if inside our event E are the two outcomes 2 and 5. So if you look back at the definition for sample space, you can see that this, or sorry, if you look back at the definition for complement, you can see that the sample space was a big part of that. Hey, so let me, before I get started here, let's actually write out the sample space. That will help us visually determine what the complement will be. Hey, so writing out the sample space. Remember, our experiment is rolling a fair die, and the sample space is just listing out all of the possible outcomes. So then all the possible outcomes would just be 1, 2, 3, 4, 5, and 6. Okay, so then for part A, if you want to find the complement of E, so EC, hey, all you have to do, hey, is look at your sample space and look at your E. Whatever is inside of your E, you're going to take that out of your sample space, and then whatever you have left is going to be in your complement. Okay, so looking at our E, we only have the outcomes 2 and 5. So if you take out 2 and 5 from your sample space, what you have left will be your complement. So then in our complement, we would have 1, 3, 4, and 6. Okay, so then now let's look at part B. Again, asking us to find EC, the complement, if E is the event of rolling an odd number, rolling an odd number. So first, just to kind of help us, let me first write out what's in E, and then from there come up with a complement. Okay, so let's first write out what's in E. Okay, so E is the event of rolling an odd number, odd number. So rolling an odd number, so in E, that would just be 1, 3, and 5. Okay, so then if you want to find the complement, again, all you have to do is just take out whatever's in your E, take that out of your sample space, and then what you have left is your complement. So then we would be taking out 1, 3, and 5 out of our sample space. So then that means what's left for our complement would be 1, or sorry, not 1. It would be 2, 4, and 6. Which you can see is just which you can see is just the even numbers. Hey, so that's why I said before the complement's kind of like the opposite of E. So the opposite of odd numbers would be even numbers. Okay, and then now for part C, it says to again find the complement if E is the event of rolling at least a 3, at least a 3. So let me, like what we did in part B, first list out the outcomes that are in our E. Hey, so if E is rolling at least a 3, what at least a 3 means, that means 3 or more, because the least you could be would be 3. Okay, so if the least you could be would be 3, that means you would want to be 3 or more. So whenever you say see at least, that means that number or more. So at least a 3 means 3 or more. So then we would want 3, 4, 5, and 6. Okay, so then going back up to our sample space, if I take that out of our sample space, what we have left will be our complement. So then in our complement, we only have the outcomes 1 and 2. Okay, so you can see with all of these, if you were to combine what's in your E and what's in your complement, notice what you would always get back. If you combine what's in your E and your complement, you're always going to get back the entire sample space. Okay, so then now let's look at part D. Hey, where it says for part A, so we'll have to refer back to part A, it says to first find the probability of E, okay, and then the probability of the complement, and then from there, it's asking us to add those two probabilities together. Okay, so it's asking us to do kind of three things here. Find the probability of E, find the probability of its complement, and then lastly to add those two probabilities together. Hey, the reason why we're doing this is to kind of help us see where this complement rule that we're going to look at, where is it coming from? Hey, so notice this is referring back to part A, part A. Hey, so the first thing we want to do is find the probability of E. Okay, so that means we'll build our fraction. Hey, so referring back to part A, okay, so that's going to be right here. Hey, so referring back to part A, if I want to find the probability of E, hey, well, in E, there's only two outcomes. Hey, so then that's going to go on top. And then remember, in your denominator for probabilities is always the total. Okay, so then this will just be 6. Hey, so then for now, let me just leave it this way. Hey, and then let's go ahead now and find the probability of the complement. Okay, so I know for the probability of the complement that there will be a 6 in the denominator, since again, that's the total number of outcomes in our sample space, since again, we had the 1 through 6. And then now let's again go back to part A and look at the complement in part A. Hey, so in part A, here's the complement that we came up with. Hey, and then notice we had 4 outcomes in our complement. Hey, so since we have 4 outcomes in the complement, the probability of the complement would be 4 out of 6. Okay, so then now let's go ahead and do this last part where it's essentially just telling us to add the two probabilities together. Well, if we want to add together the probability of E plus the probability of its complement, let's see what we would get here. Well, the probability of E, that's what we found right here. The probability of E was 2 over 6. Plus, now we want to add to it the probability of the complement. Well, the probability of the complement, that's what we found right here. Okay, so then that's going to be 4 over 6. Hey, and then just doing a little bit of arithmetic right here. Well, these two fractions have the same denominator. Hey, so then that means we can just add the numerators together. So 2 plus 4 gives me 6, and the denominator stays the same. And then 6 over 6, well, that's just going to be equal to 1. Okay, so this is where the complement rule that we're going to be looking at is coming from, is the fact, and this will always, no matter what, always be the case, that the probability of E plus the probability of its complement, that's always going to be equal to 1. Always. Hey, because of what I mentioned earlier, remember if you look back at everything that we did before, if you combine what's in the E with what's in its complement, you're always going to get back the entire sample space. So then that's why if you add the probability of E plus the probability of its complement, we're always going to get 1. Okay, so that's going to lead us to the complement rule that we see here. Hey, so you don't have to write what I'm going to write off to the side here, but let's say, let me just rewrite what we just saw, that if we add the probability of E plus the probability of the complement, we always end up getting 1. Hey, so let's say I wanted to solve it for one of these. Hey, let's say I wanted to solve this equation for the probability of, let's say, the probability of E. We could do either, but let's say we wanted to solve this equation for the probability of E. Well, if I wanted to do that, that means I need to get rid of this, the probability of its complement. So then how you would get rid of that is by just subtracting the probability of the complement from both sides. And the reason why we would do that is because that would go away. Whoops, not that. Hey, and then what we would be left with is that the probability of E, because now it's all by itself here, is equal to all of this, equal to 1 minus the probability of its complement. And this is going to be the complement rule that we're going to be using. Okay, so then that's why we did those examples to kind of see where that all of that was coming from. Okay, so we have that rule here. Hey, so it says for the complement rule, hey, if E represents any event and then EC is the complement, you can see we have two forms of the complement rule, but really the one that we'll be using will be this one here. Okay, so how you could find the probability of E, all you can do is just do 1 minus the probability of its complement. So this will be the one that we'll be using. Okay, so again, we'll use it a little bit in this section, but use it a lot more in the following section. Okay, so then let's go ahead to the next page and look at our next example, where it says that the following probability model shows the distribution of murders by type of weapon for murder cases in 2013. So we looked at all murder cases back in 2013, and then here we found the probability model for the type of weapon that was used. Hey, so for example, the probability that a murder back in 2013 used a handgun was 0.472, or about 47% of murders in 2013 used a handgun. For rifle, the probability was only 0.023, so about 2.3% of murders in 2013 used a rifle, so on and so forth. Hey, so for part A, it says what is the probability that a randomly selected murder resulted from a knife or a handgun? Knife or a handgun. Hey, so remember we saw this rule before. Whenever you see the keyword of or, that's going to tell you to add. Hey, so what we have to add together here are two events, are knife and then handgun. Hey, so then looking at the table, we just find these two probabilities and we just have to add them together. So the probability that a murder in 2013 used a knife, hey, well, that's going to be right here. That's the 0.122. Okay, so the probability of murder used a knife, 0.122, or will tell me to add, so then plus, now I want the probability of handgun. Okay, so the probability that a murder used a handgun was 0.472. Okay, and then if we just add those two numbers together, you could just type that into the calculator, but let me just give you this answer. We would end up getting 0.594. Okay, so then now for part B, it says, what is the probability that a randomly selected murder resulted from a weapon other than a shotgun? Okay, so you want other than a shotgun. Hey, so what that means, if I look at our table here, if I want the probability that a murder resulted from a weapon other than a shotgun, that means we want every other weapon except for shotgun. Hey, so two ways that we could do that. So if we want everything other than a shotgun, that means you could add up everything except for shotgun. Add up everything else except for shotgun. So that's the long way of doing it. The easier way of doing it is by subtracting. Okay, and we've done problems similar to this before. Hey, so instead of adding everything we want, what we could do is just subtract instead. Hey, so when you do this by subtracting, you always start off with the total. Hey, well, the total in this case, if you were to, again, add up all the probabilities, remember when you add up all the probabilities, it needs to add up to be 1. The 1 represents the whole, the 100%. Hey, so we're going to start off with 1. That represents everything. That represents the whole, 100%. And then what you do from here is, again, just subtract out, take out whatever you don't want. Hey, so the only weapon that we don't want, it says other than a shotgun. So we don't want a shotgun. So that's going to be the one that we subtract out since that's the one we don't want. Hey, and the probability of shotgun is 0.025. So that's the number that we should subtract out since again that's the one we don't want. We don't want shotgun here. Okay, so much easier to do it with subtraction. Okay, and then let me just give you this. If you were to type that into the calculator, we would end up getting 0.975. Hey, so this is technically using the complement rule here since we had the 1 minus. Okay, so then part C is very similar. We want the probability that a randomly selected murder resulted from a weapon that is not a rifle, not a rifle. Okay, so again, you could add everything else except for rifle together. That's the long way. Let's instead do it using subtraction, similar to what we did in part B. Okay, so you'll start off with 1. Oops, don't want to write with a highlighter. We'd start off with 1. That represents the whole, 100%. Minus, again, just take out what we don't want. So we don't want a rifle. Don't want a rifle. Hey, so then looking at our table, the probability for rifle is the 0.023. So that's the one that we should take out since, again, that's the one that we don't want. Hey, and then let me just give you this answer. If we subtract that in our calculator, we would end up getting 0.977. Okay, and then lastly for this example, it says murders using which weapons would be considered unusual? Unusual. All right, so remember with unusual, we discussed this in the previous section. What we're going to consider something as unusual, that's going to be when the probability is less than 0.05. Okay, so then what we're going to do if we're trying to see which weapons, if any, would be considered unusual is we're just going to go through the table and then any weapons that have a probability that's less than 0.05, less than 5%, would be considered unusual. So let's see if we have any that would be considered unusual. So then looking at our table, as it disappears, looking at our table here, hey, trying to find anything that has a probability of less than 0.05. Well, we have this probability that's less than 0.05. So rifle, that would be considered unusual. Also for shotgun, that's also less than 0.05. Hey, so then these two weapons are going to be the only two that would be considered unusual since these are the only two probabilities that are less than 0.05. Okay, so the two unusual weapons that we have would be rifle and shotgun. All right, so then let's go ahead to the next page, look at our next example. Hey, where it says that Harris Interactive conducted a survey in which they asked adult Americans, so 18 years or older, whether they used some sort of social media like Facebook, Twitter, etc., whether or not they used it regularly. The following table is based on the results of the survey. Hey, so let me discuss a table that looks like this because we haven't really looked at a table like this before. So this is called a contingency table. Hey, so how you would read this table, everybody in this first row here, these are going to be all the people who use social media. And they're actually in this table, they are giving us the totals, which is nice. We'll make use of that most of the time. Hey, so these are all the people who use social media. So you have 338 people total who use social media. And then here are all the people who do not use social media. And you have 192 of those people. Hey, and then here, the columns, those are going to be the age groups. Hey, so these are the people who are 18 to 34. You have 150 of those people. Then you have these people who are 35 to 44, 125 of them. These people 45 to 54, you have 140 of them. And then you have these people 55 and older, and you have 115 of them. Okay, and then here is this number in the corner. That's going to be the overall total. So that's going to be the total number of people that we surveyed. So then this number is actually going to be the number that we put in our denominator since it's the total. And then let me mention like one of these numbers here. I won't go over all of them, but like this number right here, what this group of people represents, they kind of fit into two categories. These 36 people, they are 35 to 44 years old, and they do not use social media. Okay, so that's what this group represents. Let me go over one more. Let's say this group right here, these 83 people are 45 to 54 years old, hey, and they use social media. Okay, so these 83 people are 45 to 54 and are using social media. Okay, so then now let's look at part A, where it says if an adult American is randomly selected, what is the probability that they do not use social media? Do not use social media. Okay, so then building our fraction, in the denominator would be our total, which is right here, the 530. That's the total number of people that we surveyed. Hey, and then on top is what we want, what we're looking for. So we're looking for the probability that they do not use social media. So then looking at our table, the people who do not use social media are these 192 people here. So then that's what would go on top. Hey, and then just going to our calculator to divide these two to get our decimal answer. And I'll round it to the third decimal place. So since there's just a 2 that comes after, this will round to be 0.362. Okay, or about 36%. Okay, so about 36% of the people surveyed are not using social media. Okay, so now for part B, we want, or it says, if an adult American is randomly selected, what is the probability that they are 18 to 34 years of age? 18 to 34 years of age. Okay, so then building our fraction, we'll have the total of 530 in the denominator. And then on top is what we want, what we're looking for, and we're looking for the probability that they are 18 to 34 years of age. So then going back to our table, the people who are 18 to 34 years of age, that's this group right here. Hey, so then you can see we have 150 people that are 18 to 34. Okay, and then dividing these two. Rounding to the third decimal place, this will round to be 0.283. Okay, so about 28% of people surveyed are 18 to 34 years of age. Okay, so now part C will be a little bit different. It says if an adult American is randomly selected, what is the probability that they are a 55 plus year old social media user? Okay, so they're 55 plus and they're also a social media user. That's how you want to interpret that statement. Okay, so we will still build our fraction with the total of 530 in the denominator. Hey, so then to determine what number we're going to put on top, I need to again just refer back to the table and I need to determine how many people are 55 plus and also a social media user. Okay, so how many people are 55 plus using social media? So going back to the table, the people who are 55 plus who are using social media will be these 49 people here. So these 49 people are the ones that are 55 plus and using social media. So then that should be the number that goes on top here. Okay, so then dividing those two to get our decimal answer. So again, rounding to the third decimal place, since a 4 comes after, the 2 will just stay. So we're getting a probability of 0.092. Okay, so only about 9% of people from our survey are 55 plus and using social media. Okay, so now looking at part D, very similar to part C, it says if an adult American is randomly selected, what is the probability that they are 18 to 34 and does not use social media? Okay, so that means they have to be 18 to 34 and also not a social media user. Okay, so if we were to build our fraction, the 530 goes in the denominator. And then to figure out what goes on top, I need to go back to our table and see how many people are 18 to 34 and not using social media. Okay, so then 18 to 34 and not using social media, that's going to be these 33 people here. So these 33 people are the ones that are 18 to 34 and not using social media. Okay, and then typing this into the calculator. 33 divided by the total of 530, which I'll round to the third decimal place. So since there's a 2 that comes after, this is just 0.062. Okay, so only about 6% of people are 18 to 34 and not using social media. Okay, so then now for part E, it says if an adult American is randomly selected, what is the probability that they are 55 plus years old or uses social media? Hey, so here we see a keyword that we haven't seen in a while yet. Hey, so here we're seeing the keyword of or. So remember when you see the keyword of or, hopefully we remember by now, that's going to tell us to add. Okay. And like before, if there's any sort of overlap, anything that they have in common, we're going to have to subtract that out. Okay, so our two groups here are 55 plus, and then the other group is uses social media. Okay, so we're going to add these two groups together, but again, if there's any overlap, anything they have in common, we'll subtract that out. Hey, so then going back to the table, we need how many people total are 55 plus. Hey, well, the people total that are 55 plus, we have 115 of those people, or tells us to add, so then plus. Now I want to add to that all the people who use social media. Hey, so then all the people who use social media, that's going to be this group right here. So then you can see we have 338 of those people who use social media. Okay, and then let's look back to see if we should subtract, if there was anything that we double counted. Hey, well, looking back at the table, you can see that there was a number that we double counted. Hey, so the number that we double counted is going to be where our two groups overlapped. Hey, so then you can see that we double counted these 49 people. We counted them with a 55 plus, with a 115, and then we counted them again with the people who use social media with a 338. So since we double counted this group of 49 people with the 115 and the 338, we have to subtract that out. Again, subtract any sort of overlap so we're not double counting. Okay, so here we have to subtract off those 49 people that we double counted. Okay, so then let's go ahead and add and subtract all of that. And we end up getting 404. Okay, but then remember, we still need to divide by the total. Some people sometimes forget to divide because they've done all this work of adding and subtracting, but then they forget to divide by the total. Remember that you're finding a probability. Probabilities are between 0 and 1 inclusive. So then make sure you always divide by that total of 530 in this case. Hey, and then rounding to the third decimal place, we end up getting 0.762. Okay, and then now for part F, very similar to part E, it says if an adult American is randomly selected, what is the probability that they are 18 to 34 or does not use social media? So we again have the keyword of or. That'll tell us to add. Hey, and then our two groups here will be 18 to 34. And then does not use social media is our other group. Okay, so we'll add those two totals together. And again, if there's any overlap, any number that we double count, we'll also have to subtract that out. Hey, so looking at the table, we want all the people who are 18 to 34. Hey, so all the people who are 18 to 34, that's going to be these 150 people. Or it tells us to add, so then plus what I need to add to that will be all the people who do not use social media. Okay, so then all the people who do not use social media, that's going to be right here. We have 192 of those people who are not using social media. Okay, and then let's look back to see if there's anything we have to subtract, any overlap, and any group that we double counted. Hey, and then you can see that there is a group that we double counted. We double counted these 33 people. We counted them with the 18 to 34-year-olds with the 150, and we counted them a second time with the people who do not use social media with that 192. So we'll have to subtract out that 33 that we double counted. Hey, and then let me just give you all of this. So if you were to type all of that into your calculator, you would end up getting 309, which again, you still have to divide by the total of 530. And then let me just give you this decimal answer. If you were to divide these two numbers in the calculator, we would end up getting 0.583. Okay, so then let's go ahead to our last example. So this is very similar to the previous example that we worked on. So if you want to try this problem on your own, feel free to do that. Pause the video and then just check your answers at the end of the video. Hey, but it says that the following data represent the number of drivers involved in fatal crashes in the United States in 2013 by day of the week, so the day of the week that the fatal crash happened, and by gender. Okay, so the gender of the person driving. Hey, so here you have by the days of the week, so the day that the fatal crash occurred, along with the totals. Hey, and then you also have it broken down by gender. So this is going to be all the crashes that involved a male driver, and then here would be all of the crashes that involved a female driver. Hey, and then this number that you have in the corner here, that's again going to be your overall total. Okay, so that's how many fatal crashes we had total back in 2013 in the United States. Hey, close to 40,000. Hey, so for part A, it says to determine the probability that a randomly selected fatal crash involved a female. Hey, so we will build our fraction, and in the denominator will again be that total, the 39,900. And then on top will be the total number for female. Okay, so the total number of crashes that had a female is going to be this number here, the 13,989. Okay, so then putting this into our calculator, okay, and then rounding to, let's say, the third decimal place again, since there's a 6 that comes after, the 0 will get bumped up to a 1. So we're getting 0.351. Hey, so what that's telling us is that 35% of fatal crashes involved a female driver. Hey, so then you can use that to actually figure out the percentage of fatal crashes that involved a male driver. So if 35%, about 35% of fatal crashes involved a female driver, that means the remaining 65% involved a male driver. Okay, so then now let's go ahead and look at part B. It says to determine the probability that a randomly selected fatal crash occurred on a Saturday or involved a male driver. Hey, so we have our keyword of or, which will tell us to add. Hey, and then the two groups that we're dealing with here. So we want the fatal crash to have occurred on a Saturday and then involved a male driver. Hey, so then first thing we're going to do is add up these two totals. And again, like what we've seen before, if there's any sort of overlap, we'll have to take care of that double counting by subtracting. Hey, so first we need the total number of crashes that occurred on a Saturday. Hey, so that's going to be right here, 7260. Okay, or tells us to add. And then now I want the total number of crashes that involved a male driver. Okay, so male driver, the total there will be the 25,911. Okay, and then let's see if there's anything we should subtract, any sort of double counting that occurred. Hey, so then looking at this, there was a group that we double counted. That's going to be this group of people here. We counted them with the Saturday. this number, and then we double counted them again with the males. Okay, so then we have to subtract out that overlap where we double counted the 47, 49. So we'll minus that out. Hey, and then let me just give you this number. So if we add and subtract all of this in our calculator, we end up getting 28422, which we would have to divide by our total of 39,900. And then let me go ahead and type this into the calculator to see what we'll get as our decimal answer. Okay, and then rounding to the third decimal place, we would end up getting 0.712. Okay, so about 71% of fatal crashes happened on a Saturday or involved a male driver. Okay, so now for part C, we want to determine the probability that a randomly selected fatal crash occurred on a Monday and involved a male. Okay, so building our fraction, I know we'll have the total in the denominator. Hey, and then here we're trying to find the probability that the crash occurred on a Monday and involved a male driver. Hey, so Monday and male. Hey, so I'll have to go back to the table, and to figure out what goes on top, I need to see how many crashes occurred on a Monday and involved a male driver. Hey, so going back to our table, it needed to happen on a Monday and involve a male driver. So that's going to be this right here. So we had 3,178 crashes that happened on a Monday and involved a male driver. Okay, and then from here we just type this into the calculator. To get our decimal answer. So for this one, if we want to round to the third decimal place, since there's a 6 that comes after, this is going to get bumped up. So instead of 0.079, this will get bumped up to 0.080. Okay, so about an 8% chance that a fatal crash will happen on a Monday and involve a male driver. Okay, so then now let's look at part D. We want to determine the probability that a randomly selected fatal crash occurred on a Thursday or, okay, so add, or involved a female. Okay, so occurred on a Thursday or involved a female. Okay, so our two groups will be Thursday and then involved a female driver. Hey, so what we'll do, very similar to before with the other or problem we saw, we're going to add up the two totals for Thursday and then also for female. And if there's any sort of double counting, any sort of overlap, we'll need to make sure to subtract that out. Hey, so first I need the total for Thursday. Hey, so the total number of crashes that occurred on a Thursday, this number right here, the 5228. Okay, or it tells us to add. And then now I want to add to it the total number of crashes that involved a female driver. Okay, so the total number of crashes that involved a female driver, that's going to be right here, the 13,989. Hey, and then lastly, we will have to subtract. There was a group that we double counted. Hey, so then going back to our table to see where our overlap is, where we double counted, hey, that's going to be right here, the 1839, because we counted those people with the Thursday, the 5228, and then we counted them again with the females, the 13989. So we'll have to subtract out the overlap of 1839. Okay, and then let me just give you this number. If we were to add and subtract all of this in the calculator, we would end up getting 17378, which of course we must divide. Don't ever forget, always divide by the total. And then let me just give you this decimal answer. So if we were to type this into the calculator, we would end up getting 0.436. Okay, or about 44%. So about 44% of fatal crashes occurred on a Thursday or involved a female driver. All right, so then lastly for part E, asking us would it be unusual? So again, unusual, that means less than 0.05. So we'll have to find the probability, and then if it's less than 0.05, we'll consider it unusual. Okay, so would it be unusual for a fatality to occur on a Tuesday and involve a male driver? So Tuesday and a male driver. Okay, so let's go ahead and find that probability in order to see if it would be considered unusual. Okay, so in our fraction, we'll have the total in the denominator. And then to determine what goes on top, I'll need to go back to the table and see how many crashes occurred on a Tuesday and involved a male driver. So it had to happen on a Tuesday and it had to involve a male driver. Okay, so if it had to happen on a Tuesday, that's right here, but it also needed to involve a male driver, so that's going to be this group right here. So we had 3,280 crashes that happened on a Tuesday and involved a male driver. Okay, so then that number will go on top. Okay, and then let me go ahead and actually type this into the calculator to see what we'll get as our decimal answer. And I'll round it to the third decimal place. So since there's a 2 that comes after, the 2 will stay. So we're getting 0.082 as our probability. Hey, so we'll have to see now if this is going to be considered unusual. So here, this is a probability. You want to compare it to 0.05. So 0.082, that's going to be bigger than 0.05 because this is about 8%, whereas this is 5%. So since the probability is bigger than 0.05, this is not going to be considered unusual. So we'll say no, because it's asking would it be unusual. So we'll say no, since the probability is greater than 0.05. Boxes. Okay, so then that's it for section 5.2. This section isn't too bad either. I think people kind of like this section. Really, the main two rules here are those addition rules. So again, whenever you see the keyword of or, that is going to tell you to add. But again, just be careful if there's any sort of overlap, anything they have in common, make sure you also subtract that out to take care of any double counting. Okay, so those are kind of the two addition rules that the two main takeaways from this section will be those two different addition rules.